Hi, I am M.Muruganandam, working as an associate professor in the Department of Marine Engineering in PSM College of Engineering and Technology, Melathiliu, Tirunelveli district. This lecture is on mechanical vibrations, where I am going to explain few problems on free vibrations of single degree of freedom systems. It is a tutorial session. Free vibrations. Before going into these problems, let us understand the basics of free vibrations. First, I explain about vibration. The motion of any body which is repeating itself over a period of time is called a periodic motion or vibration. There are two kinds of vibrations. One is free vibration, two is forced vibration. The free vibration is not caused by any external forces, whereas a forced vibration is caused by external disturbing forces, repeatable forces, such as unbalance in the mass of the rotor, etc. Now, this session is on free vibration. Let us go to the topic on this vibration, where the problem 1 is given as below. If x1 is equal to 5 sin 3t and x2 is equal to 4 sin 3t plus pi by 6, find x is equal to x plus x1 plus x2. Express your result as x is equal to a sin 3t plus phi, where a is a constant, phi is called phasor angle. Here x1, x2 are the displacement of the vibrating systems. x1 and x2 are displacements. T is time, hence we have a displacement time function. Displacement as a function of time. Displacement of system 1 and displacement of system 2. Where 5 is the amplitude of the displacement. 5 units, it may be millimeter or centimeter or meter, whatever it may be. 3 is the angular velocity, angular frequency of the vibration. It is given in radian per second units. Pi by 6 is the phase angle. Now, the problem is to express these two different displacement time functions in terms of the expressions A and B, where A and B are constants, phi and psi are phase angles. Let us see how can we do it. The solution is progressing as follows. The first function, displacement time function, x1 is equal to 5 sin 3t, can be plotted in this graph. This is called displacement time graph, where ordinate is the displacement, x in meter, the abscissa is time in seconds. as shown here, the blue line is the displacement function 1, sine function. At time t is equal to 0, displacement is 0, and as the time progresses, displacement increases, and again displacement decreases. So the displacement of the system with respect to the equilibrium position, 0 position, is shown here as time displacement graph, where 3 is the frequency, angular frequency, which is in radian per second. As it can be seen, 5 is the amplitude of the displacement. If you can see in the ordinate, the blue curve, the maximum value of the blue curve is 5 meter. The frequency, angular frequency, is 3. What is the meaning of this? For every 1 second, 3 radians of the angular displacement takes place. What is the relation between this omega and this time displacement curve? If we see the period of vibration, that is the time taken for one complete cycle of vibration, is called period, can be obtained using this angular frequency, where period capital T is 2 pi upon omega. Substituting omega is equal to 3 radian per second, we obtain the period of the vibration T is equal to 2.094 seconds. That is the time duration between consecutive points of correspondence. We start from the time t, small t, is equal to 0.5 seconds to the corresponding point, maximum point, that is 2.094 seconds. The maximum to maximum value of x1 is period, or minimum to minimum, that is the time duration between consecutive points of correspondence of the curves, that is angular frequency, time period t. Okay, then what is the phase angle? In the function 1, x1 displacement function 1, phase angle is 0. Here in the displacement function 2, the phase angle is pi by 6. What does it mean? The displacement time graph of the function 2 is shown here as green curve. At time t is equal to 0, the displacement is not 0. Displacement is finite. It shows the initial condition, whereas for the first function, the initial condition is such that the system starts from the equilibrium position 0, whereas for the second function, the displacement is finite, that is there is an initial displacement function. So the system, vibrating system, can start from either the 0 initial condition, that is equilibrium condition, or a finite displacement from equilibrium conditions. The second one is such a finite initial displacement condition. Alright, now if you see the two curves, the first difference is that the x1 curve has higher amplitude. The maximum displacement of the function 1 is 5 meter, whereas the maximum displacement of the function 2 is 4 meter. The amplitude 4 is the amplitude of displacement. Second difference is that the blue one advances the green one. The x1 function advances the green one. Sorry, lags the green one. First, the maximum displacement of the green function takes place first at the earlier time period. After that, only the maximum of the blue one, that is x1 function, takes place. We call it as time lag. How can we calculate the time lag? That can be calculated using this phase angle. For 2 pi radian of the displacement, the time taken is capital T, period of the vibration. So for this much of angle, phase angle, how much is the time taken? That is 0.1745 seconds. That means x2 leads x1 by 0.1745 seconds. Before the x1 reaches the maximum, the x2 reaches the maximum. The difference in the advanced time is 0.1745 seconds. Either it can be given in terms of the angular displacement pi by 6 radian or in terms of time 0.1745 seconds. So the time lag or time lead, x2 is leading the x1, or we can say x1 is lagging x2. In both the ways we can say. So our objective is to write these two functions x1 and x2 in terms of x, where x is equal to x1 plus x2. Again we have to write this equation in a form given in the previous page as x is equal to a sin 3t plus phi and x is equal to b cos 3t minus psi. Solution is continued here. X has two terms, term 1 containing 5 sin 3t, term 2 contains 4 sin 3t plus phi by pi by 6. I expand the term 2, which is shown in red color, using the trigonometric identity. Sin a plus b is equal to sin a cos b plus cos a sin b. Now I add these two terms, I obtain x is equal to 5 2 root 3 sin 3t plus 2 cos 3t. Using this expanded equation sin a plus b, now I write the original equation as shown here. This is the original equation, which is displacement equation, which is rewritten here using this expansion form, sin a plus b expanded form. Now my objective is to write this x in terms of a sin 3t plus phi. Once again I expand the right hand side of this equation using the same trigonometric identity, sin a plus b. I obtain x is equal to a sin 3t cos phi plus a cos 3t sin phi. There are two equations. Equation 1 obtained from the given equations x1 and x2, where x is equal to x1 plus x2. I have expanded this term 2 using this trigonometric identity. I obtained equation 1. Equation 2 is obtained from the required solution. The required form of the solution is x a is equal to sin 3t plus phi, again which has been expanded using the same trigonometric identity, sin a plus b equation given here, which is given as equation 2. Comparing these two equations 1 and 2, where sines and cosines are linearly independent functions, Hence, we can equate the coefficients of sines and cosines of equations 1 and 2, from which we will obtain a sin phi is equal to 2, a cos phi is equal to 5 plus 2 root 3, equations 3 and 4. Now I square on both the sides of equations 3 and 4 and sum them up. We obtain a is equal to 8.6972 meter. I divide the respective sides of equations 3 and 4 and taking the inverse of tan, I obtain phi is equal to 0.232 radian. By squaring on both the sides, on the left hand side, if you square it, you will get a square sin square phi, a square cos square phi, and I am going to sum it up, summing up equations 3 and 4. A square sin square phi plus a square cos square phi will give a square, where sin square phi plus cos square phi is equal to 1. Taking a square common outside, sin square phi plus cos square phi is equal to 1, from which by taking the square root of that equation I can obtain a, that is equation 5. Now I divide the equation 3 by equation 4. By dividing equation 3 by 4, a sin phi by a cos phi on left hand side of the equation, where a and a get cancelled, sin phi by cos phi will get tan phi. Now I take the inverse of the tan function, from which I obtain phi is equal to 0.232 radian, which is equation 6. Hence now I can write x using equations 5 and 6 as a sin 3t plus phi, where a is equal to 8.6972 meter, that is the amplitude of the displacement. Maximum displacement of the system is called amplitude of displacement, and 0.232 is the phase angle, radian. 0.232 radian is the phase angle. Hence the problem A is solved. Problem B can also be solved in a similar manner by following a similar procedure. I can obtain the constants B, which is equal to 8.6972 meter, and the phase angle psi 1.3388 radian. The solution is given here as B, so equation B. So the equations A and B are the required solutions for the given problem. The solutions A and B can also be plotted in the time displacement diagram as shown here. I have plotted 4 different functions. First one is green, which is 8.6972 sin 3t, which is a pure sine function where the phase angle is 0, is that the initial condition is 0. Initial displacement is 0. The red one is with the phase angle, is that the initial displacement is a finite one. What is the difference between the two functions, green function and red function? Both of them have the same amplitude of vibration, whereas the red one is advancing the green function with a phase angle of 0.232 radian, which is shown here. And for the second problem, x is equal to 8.6972 sin 3t, which is again solutions A and B can also be plotted as a graph in time displacement diagrams as shown here. The green function, which is green colored function x is equal to 8.6972 sine 3t is a pure sine function where the initial displacement is 0. The angular frequency is 3 radian per second. Whereas the red colored function has the same amplitude as that of the green colored one. The difference between these two is in the phase angle. The red colored function is advancing the green colored function by 0.232 radian, or we can also say that it has a finite initial condition. The initial condition is not 0. Initial displacement of the red colored function is not 0. The system starts from a finite displacement. Okay. Now the solution of the second problem, which is a pure cosine function, blue one is pure cosine function. It starts from the maximum displacement. Initial condition is not 0 again. Whereas the fourth curve, the light blue curve, is different from the dark blue curve by the phase angle. If we can see, the dark blue is lagging by an angle of 1.3388 radian. So the plus 0.232 plus the phase angle indicates a leading function, and minus phase angle indicates a lagging function. This is the result of the problem 1. We go to the second problem. Description is given here. A mass executes a simple harmonic motion about its equilibrium position at a frequency of 4 Hz according to the given function. Y of t is equal to a cosine omega t plus phi. An accelerometer measures the maximum acceleration of the mass to be 15.62 meter per second square. Solve for the amplitude of oscillation and the maximum velocity of the mass. If t is the time period and mass was at equilibrium at time half of the time period, find the displacement in millimeters at time 2 times the period, 2/3 of the period of the vibration, 2t upon 3. It is given that the frequency of the vibration is 4 Hz. This is the cycles per second, 4 Hz, 4 cycles per second. One cycle consists of 2 pi radians of motion, angular motion. Hence, I can find the angular velocity, angular frequency using this frequency f using 2 pi f. Omega is equal to 2 pi f. F is 4 Hz, hence I can find the angular frequency omega is 25.1327 radian per second. Equation number 1. The displacement of the mass is given by the function y is equal to a cosine omega t plus phi, where a is the amplitude of the displacement, omega is angular frequency of the vibrating motion, t is the time with respect to which the displacement of the system is measured, phi is the phase angle. Let us take this function as equation 2. Velocity of the mass is obtained by differentiating the equation 2 with respect to time. If I differentiate the equation 2 with respect to time, I obtain the velocity of the vibrating system. A is constant, phi is constant, only variable is time. So differentiating it, I obtain Differentiating cosine omega t plus phi, I obtain sine omega t plus phi. Differentiating omega t, I obtain omega. That is differentiating cos omega t plus phi, I obtain minus sine omega t plus phi, and differentiating omega t, I obtain omega. Hence, I have the velocity function as minus a omega sine omega t plus phi. Equation number 3, velocity function is taken as equation number 3. Acceleration of the mass is obtained by differentiating the velocity function once again by time t. A of t, that is acceleration of the system, which is differential of velocity with respect to time, dv by dt. Once again, a is constant, omega is constant, phi is constant, the only variable is time. Differentiating the sine function, we obtain the cosine function. Differentiating the product omega t, we obtain omega. Already there is an omega, so omega square minus a omega square cosine omega t plus phi, which is equation number 4. From equation number 4, for maximum acceleration condition, when will it have the maximum acceleration? Whereas here a is the amplitude of the displacement, a omega is the amplitude of the velocity, a omega square is the amplitude of acceleration. What is the amplitude of displacement? Maximum displacement, a. What is the amplitude of the velocity? Maximum velocity, a omega. What is the amplitude of acceleration? Maximum acceleration, a omega square. So a max is a omega square. We know the values of a and omega. So this is given, the maximum acceleration is given, a omega square is equal to 15.62 meter per second square. 15.62 is the maximum acceleration given. The maximum acceleration of the mass is 15.62, from which we go to find out the constants a and omega. Omega is already found out, that is 25.1327 radian per second, from which I can find out the constant a. Substituting omega from equation 1, that is 25.1327 radian per second, into equation 5, I obtain the constant a, which is the amplitude of vibration or amplitude of oscillation, which is 0.0247 meter. Let us take this as equation 6. From equation 3, maximum velocity is given here. From this equation 6, the maximum velocity is a omega. The maximum velocity can be found from equation 3, which is a omega. Here a is known, 0.247 meter, and omega is known, which is 25.1327 radian per second, from which I obtain V max, that is equation number 7. The time period of oscillation is obtained from the equation, that is time period is inverse of the frequency of oscillation. Time period is the time taken for the completion of one cycle of vibration, whereas frequency is number of cycles per unit time. So the inverse of the frequency is the time period. The frequency is given, that is 4 Hz, from which I can obtain the time period, which is 0.25 seconds. When time is equal to t by 2, that is half of the period, mass is in equilibrium position. The first two questions have been answered, that is amplitude of oscillation and maximum velocity of the mass. Amplitude of oscillation is 0.0247 meter from equation 6. Maximum velocity of the mass is 0.6208 meter per second from equation 7. Next one is, if time t is the time period and mass was at equilibrium at t is equal to t by 2, find the displacement at the time 2t by 3. So the mass is at equilibrium when time t is equal to half of the period. For the equilibrium position of the mass, y is equal to 0, displacement is 0. Is that when y is equal to 0, we have cos omega t by 2 plus phi is equal to 0, where I have substituted t is equal to t by 2. From equation 8, phi is equal to pi by 2 minus omega t by 2. Is that phi is equal to minus 1.57079 radian or minus pi by 2 radian. Okay. Now displacement of the mass when time t is equal to 2t by 3 is given by equation 2. Y of t is equal to a cos omega t plus phi. I substitute t is equal to 2t by 3, omega is equal to 25.1327 radian per second, a is equal to 0.247 meter, and phi is equal to minus pi by 2 radian. In equation 2, I obtain the displacement of the mass at time t is equal to 2t by 3 as 0.2467 meter or 24.67 millimeter. So this is how the given problem is solved for amplitude of oscillation, maximum velocity of the mass and displacement of the mass. Problem 3 is a disk of the polar moment of inertia 40 kilogram meter square is mounted at the end of a shaft 1000 Newton meter per radian. When immersed in a viscous liquid, the disk undergoes torsional vibrations with damping ratio 0.05. What is the value of the damping constant for this case? What is the frequency of the damped oscillation? How many cycles does it take for the initial amplitude to decay by 97%? If you see the system which is shown here, there is a fixed support, there is a shaft, there is a disc at the bottom end which can twist and untwist. The alternate motions of twisting and untwisting is called torsional vibration, and this disc is immersed in a viscous liquid which acts as a damper. If you see any real system in practice has various components. As shown here, for this system we have support is a component, shaft is a component, disc is a component, viscous liquid is a component. In modeling the vibrational system, we simplify the real system in such a way that we take one of the component as a mass, another component as a spring, another component as a damper. How do you select one component as a mass. For example, here the disk is taken as the mass component. It is the reason for which here we give the polar mass moment of inertia of the disk. It is an inertial component. The shaft is taken as a spring component, torsional spring component, for which the stiffness is given. The liquid is taken as a damping component. How do you identify the shaft is a spring component, disk is a inertial component, liquid as a viscous component, damping component? It is based on the relative magnitudes of the mass, stiffness and damping coefficient of the various components. In this system, when compared with the mass of the shaft, the mass of the disk is higher, much higher. Is that the disk is much heavier than the shaft. Hence, even though the shaft has a mass, its mass is negligible, neglected. Similarly, in any real system, all the components have mass. If there are 5 different components, for example, in a system, all the 5 components will have the mass. But all these 5 components will not be taken as a mass element in the vibration analysis. These are the 3 different basic elements we use in vibrational analysis: mass element, spring element and damper element. The mass element is one among these 5 components which has the highest mass. So the heaviest component will be modeled as mass element of the system, vibrating system. Similarly, all the components in a real world are elastic in nature. Upon the application of a load or a force, every component will deform. But only one of the component is taken as the spring element in the vibrational system analysis, based on the reason that the elasticity of that component is much higher than the elasticity of other components. That is, when compared with the shaft component, the elasticity of the disk component is much smaller. It can be assumed as a rigid component, whereas the shaft is assumed as a spring component. It has highest elasticity among these 4 components: support, shaft, disk and damping liquid. The motion of any body requires energy. So all the bodies which are in motion in a vibrating system have energy, and they dissipate the energy in the form of heat, viscous damping. So the energy which is lost during the motion is modeled as a damping element. The energy lost by the shaft, the energy lost by the disk during the vibrating motion is absorbed by this element called liquid, viscous liquid. It is taken as torsional damper. Accordingly, we have the polar mass moment of inertia of the disk, which is given here as 40 kilogram meter square. The torsional stiffness of the shaft is given here as 1000 Newton meter per radian. K is given here. The torsional damping coefficient is taken as C. Using these three parameters, polar mass moment of inertia of the disc, which is equivalent to mass in a linear vibrating system or rectilinear vibrating system. Stiffness K is as similar to the stiffness of rectilinear vibrational system. C is the damping coefficient for the torsional vibration, which is equivalent to the damping coefficient of a rectilinear vibration system. Whereas in a rectilinear vibration system, the displacement is linear, whereas here in a torsional vibration system, the displacement is angular displacement, theta, with respect to time. In the previous two examples, problems which I have explained, displacement is shown here as x, rectilinear displacement. Here the displacement is theta, angular displacement. Either twisting or untwisting of this disc take place with respect to this fixed support as shown here. The repeated twisting and untwisting of this disc with respect to this fixed support is called the torsional vibration. The objective is to find the damping constant for this case, that is, we could find the value of C, we got to find the frequency of the damped oscillation, that is F, we got to find. Then we got to find how many cycles it take for the initial amplitude to decay by 97%. It is a damped oscillation, hence with respect to damped vibration, with respect to time, the amplitude of vibration will decrease. We would find out the number of cycles by which the initial amplitude is decreased with 97%. This is the equation of motion of the system minus tau s, that is the twisting force due to the spring element shaft, minus tau d, the twisting force due to the damping element, that is viscous liquid, is equal to inertia force J theta double dot. J is polar moment of inertia and theta double dot is angular acceleration, which is shown here in the right side. The systems of force equilibrium free body diagram of the system is shown here. The shaft is given, shaft gives a spring force of k theta, that is twisting force due to the spring element is k theta, where k is the stiffness of the spring shaft and theta is the angular displacement. Stiffness is the force required to deform or deflect an element, mass element, by unit displacement. Whereas the damping force is the force required for making an unit velocity of the element. Tau d is proportional to velocity, where the proportionality constant is damping coefficient. Tau s is proportional to theta, where proportionality constant is k. These forces are acting in a direction opposite to the direction of the motion of the disc. The disc motion is shown here as counterclockwise when we see from the top side, whereas the forces due to the spring element and damping element are acting in the clockwise direction when we look from the top view. Hence the equation is written here as shown here. bringing all the terms in one side of the equation, j theta double dot plus c theta, that is due to the damping force, c theta plus k theta, that is due to the spring element, is equal to 0. Dividing the entire equation by j, I obtain the equation as shown here, which is the equation of motion of the free vibration of the given torsional system, from which I can find the angular frequency corresponding to resonance in the absence of damping, that is kt by j. Now I am going to find out another angular frequency with damping, that I shall explain in the next slide. Without damping, this is the angular velocity, angular frequency. It is also called natural frequency. At this natural frequency, when the system operates, the amplitude of vibrations becomes maximum. The vibrational frequency corresponding to the maximum displacement of the system is called resonance frequency or natural frequency. In the absence of damping, it is shown here, which is given by square root of k by j, where k is the stiffness of the shaft, j is mass moment of inertia of the disc. The solution which is applicable for this free vibrational equations of motion is theta is equal to e power lambda t. Here the system can have three different solutions. The value of the damping coefficient may be equal to the critical damping coefficient or less than critical damping coefficient or greater than critical damping coefficient. The critical damping coefficient is equal to 2 square root of jk. From the given values of the j, polar mass moment of inertia is 40 kg per meter square and k is 1000 Newton per meter. I can obtain the critical damping coefficient, which is 400 Newton meter per radian per second. It is given that the damping ratio is 0.05. That is, damping coefficient is smaller than the critical damping coefficient. Hence, it is an underdamped system. In an underdamped system, the system will vibrate, but the amplitude of vibration will die down. That is the condition. Hence, the damping coefficient can be obtained from this damping ratio. Damping ratio is 0.05 and the damping coefficient at critical condition is 400 Newton meter per radian per second, from which I can obtain the damping coefficient as 20 Newton meter per radian per second. Since the damping is light damping, that is under damping, C is less than Cc, the roots of this equation are complex and conjugate with each other. The roots of this equation, the roots of the equation of the motion are complex and conjugate. This equation is obtained from substituting theta is equal to e power lambda t in the equation of motions. In this equation of motion, we have the angular acceleration theta double dot, angular velocity theta dot and angular displacement theta. The equation of the displacement which is applicable for this system is given here, e lambda t, where lambda is the frequency of oscillation and t is time. By differentiating this theta with respect to time, I obtain angular velocity. Again, differentiating the velocity, I obtain angular acceleration. Substituting these values here, I obtain the roots of the equation for roots of this problem. which are complex and conjugate. It is called characteristic equation for this problem, where the lambda is given here in terms of damping coefficient C, polar moment of inertia J, and critical damping coefficient Cc. The critical damping coefficient is obtained in such a way that the radical of this solution is equal to 0. Here I have an equation Cc is equal to 2 square root of Jk. This equation has been obtained by using the relation that the radical of this equation, that is C by 2j whole square minus Cc by 2j whole square is equal to 0. Using that relation only, I obtain the relation for Cc, from which I can obtain the displacement function, displacement time function, which is a general solution, where I can see the omega d, which is a damped natural frequency of damped oscillation, which is given by this term in the radical form, square root of Cc upon 2j whole square minus C upon 2j whole square. Substituting the values of critical damping coefficient, which is 400 Newton meter per radian per second, and J, that is 40 kilogram per meter square, and C 20 Newton meter per radian per second, I obtain the frequency of the damped vibration is 4.9937 radian per second. I have plotted the solution here, where theta n, I can plot this equation in a time displacement diagram again, where abscissa is given with time variable t in terms of seconds. The ordinate is given in terms of the angular displacement theta with the units of radian. The problem is, let the initial amplitude is theta L and the final amplitude is theta M. For the initial amplitude to decay by 97%, the ratio theta L minus theta M by theta L is equal to 9.97. Let us take theta n corresponding to the maximum displacement at a particular time is given by exponential of minus C upon 2jt using the given displacement function, general solution function. Theta n plus 1, that is the amplitude of the vibration of the consecutive cycle, is theta n plus 1. The difference between these two functions is the time period 2 pi by omega d, where omega d is the damped frequency of vibration. The ratio of this theta n plus 1 by theta n is given here. This factor is constant. This is called decaying ratio, decaying rate of decay of vibration, theta n plus 1 by theta n. For any two consecutive maxima, theta n and theta n plus 1, this ratio is constant, where C is damping coefficient of the system, J is polar moment of inertia of the system, omega d is damped frequency of vibration. All these three quantities are constants, hence the rate of decay of the vibration is also constant. If x denotes the number of cycles in which the initial amplitude decay by 97%, then I can write theta m by theta l, that is the final amplitude by initial amplitude, as exponential of minus pi cx by j omega d. For one cycle of decay, this much of decay rate. For this many cycles of x cycles of vibration, how much is the decay? That should be equated to the given 0.97, from which I can obtain x is equal to 11. That is, for it takes 11 cycles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So after 11 cycles, the initial amplitude, that is 1 radian given here, is reduced to 0.3 radian, that is 3%. Initially 100%, the decay is 97%, final is 3%. If the initial value is 1 radian, the final value is 0.3 radian. How many cycles it takes? This is the damped free vibration. Upon the progress of the time, the amplitude of vibration decreases. So this is the result of the problem 2. Problem number 4 is on the natural frequency of oscillation of a liquid column in a U-tube manometer, where the left limb and right limb have different cross-sectional areas, small a and capital A respectively. The total length of the liquid column is L. Like was shown here, the U-tube manometer, where there is a liquid for which the density is rho, density of the liquid. The left limb has cross-sectional area of small a, and right limb has the cross-sectional area capital A. So the mass of the liquid in the left limb can be obtained by multiplying the volume of the column and density, that is rho AL. For the right side limb, the mass is rho multiplied by A multiplied by L, that is total length is L, total length of the liquid is L in the U-tube, minus L will give the net length of column in the right limb. So mass in motion, which is given here, force of the gravity tends to restore the liquid level to its equilibrium position. This is in the first one, I have shown the manometer liquid in equilibrium condition. In the second one, it is shown in vibratory condition. With respect to the equilibrium position, the left limb liquid rises up and right limb liquid rises down, falls down. The force of gravity tends to restore the liquid level to its equilibrium position. So the gravity force is acting as a spring force, gravity force. The raise of liquid mass in left leg is equal to fall of liquid mass in right leg from the continuity condition. The distance by which it is rising in the left limb is x1, the distance by which falling is x2. Using the area of cross section of the limbs A and A, small a and capital A, rho x1A is equal to rho x2A, from which the fall distance x2 can be written in terms of rise distance x1 for a single degree of freedom system. Again, writing the equation of motion where the gravity force acts as the spring force that restrains the inertial the force due to acceleration, that is inertia force mx1 double dot. The spring force due to the gravity can be written as rho g x1 plus x2a. x1 plus x2 is the total length of the column in the columns of limb, left limb and right limb. A is the cross sectional area, rho is the density, that is the spring force. mx1 dot, the double dot, is the inertial force due to the liquid mass. Writing it using the relation for x1 plus x2. x1 is already written as there is a relation between x2 and x1 given here, from which I can write x2 in terms of x1 and finally the equation can be written in terms of x1, from which the natural frequency can be written as the coefficient of the displacement x1, that is k by m. So that's all about the natural frequency of the liquid column which is vibrating inside a U-tube manometer. Thank you.